Welcome to Math Stack Exchange Tuesday. This is the first video of the series, and in this series we would look at some interesting questions asked on Math Stack Exchange and appreciate the excellent answers to those questions. This week's highlighted post would be why px equal to 0 is equivalent to px over p prime x equal to 0 for every polynomial p. The corresponding post number on Math Stack Exchange is 4345516. The link is also provided in the description. In this question, Aeron Speedy asks, let's say px is x to the fourth power plus x cubed plus x squared plus x, and then the derivative p prime x is 4x cubed plus 3x squared plus 2x plus 1. The solutions of px equal to 0 are -1, 0, -I, and I. And for px over p prime x equal to 0, the solutions are the same. Does it happen for all polynomials? Let's look at another example. Assume that px is x squared minus 4, then the roots of px equal to 0 are simply x equal to -2 or 2. P prime x is 2x, and px over p prime x is x squared minus 4 over 2x. And the roots of px over p prime x equal to 0 happen to be x equal to -2 or 2 as well. So is it true that px equal to 0 is equivalent to px over p prime x equal to 0, in the sense that they share the same roots for any px? We have a great answer from Mike. First, we claim that when a polynomial px has a root r with a multiplicity of k, where k is some positive integer, then r would also be the root of p prime x with a multiplicity of k minus 1. How do we prove that? But before doing so, let's explain what multiplicity is. The multiplicity of a root is defined as the number of occurrence of the root in the polynomial equation. For example, if px is x minus 1 squared times x plus 2 equal to x3 minus 3x plus 2 equal to 0, then x equal to 1 is the root of multiplicity of 2, and x equal to -2 has a multiplicity of 1. Now comes the proof for the claim. If r is the root of px with a multiplicity of k, then we can rewrite px as x minus r to the kth power times qx, where qx is a polynomial so that it is non-zero at x equal to r, or in other words, the polynomial qx does not have r as its root. Then by product rule, we have this expression of p prime x, from which we can deduce mainly from the first term that p prime x would still have x equal to r as the root, but with a multiplicity of k minus 1. Or you can say that the multiplicity is reduced by 1. Back to the main task. We have to decide if px equal to 0 and px over p prime x equal to 0 have the same roots. We generalize to consider all the distinct roots of px, and rewrite both px and p prime x as shown here. We use the pi notation to carry out the product with index running from 1 to m over all roots. Px here is simply the product of all roots, counting repeated multiplicity, and p prime x is only different from px with k replaced by k minus 1, and small px works just like qx in the previous discussion, so that small px is not equal to 0 at the roots of big px. Dividing px by p prime x, we have the following expression. We can see that px over p prime x is made up of factors representing all the roots of px. As looked before, pri is non-zero for all I. Hence, px and px over p prime x will have the same roots from R1 up to Rm as px. But there is a caveat. If the multiplicity of a root is greater than 1, then the division is undefined at the location of roots x equal to Ri. You can see that for the division of the second factor will not be possible because it would be dividing by 0 at the location of the root. Let's say px is x squared, p prime x is 2x, then px over p prime x equal to x squared over 2x is not strictly equal to x over 2 or 0 because we cannot divide it by 0, so x cannot be 0 as well. However, if k is 1 for any I so that they are all single roots, then it is still applicable, or as David hints, invoke the notion of limit and fill in the holes. You can see that for the function x squared over 2x, there is a hole at x equal to 0. But if we take the limit, we can see that this is actually at 0. Thank you for your patience. Please share your thoughts in the comment section below. Register an account on StackExchange to see more quality questions and answers. And if you like this video, please remember to like and share and subscribe to my channel. Thank you.